Today, I want to talk about the concepts your professors teach and still can't remember. The kind of concepts that are impossible to keep straight in your head. This time, from Earth Science. In this video, we tackle how oxygen isotopes record Earth's climate. Out of the 118 elements on the periodic table, oxygen is an element most of us have known most of our lives. Take a deep breath in. The air pushing your lungs right now is around 20% oxygen. Not only does it breathe life into each of us, but it lets Earth scientists breathe life into the rich climatic history of Earth. Oxygen allows scientists to understand Earth's climate from hundreds of millions of years ago, but the basic relationship between oxygen isotopes and Earth's temperature seems to be a particularly slippery concept for even the highly trained minds of Earth science professors to keep a firm grip on. As an Earth science student myself, I have had many humanizing conversations with my professors where we have both tried to piece together the science and laughed about how at least one of us in this conversation should be able to remember. So what are oxygen isotopes, and what can they tell scientists about past climates on Earth? I hope this video will cement the basic relationship between oxygen isotopes and Earth's climate, no matter if you are a visual, auditory, kinesthetic, or reading or writing learner. Visual learners, this one's for you. Here are three of Earth's reservoirs, or places oxygen is stored as the O in water's chemical compound H2O. In the oceans, oxygen exists as liquid water. In the atmosphere, oxygen exists as water vapor. And in ice, oxygen exists as solid water. Water in the oceans evaporates into the atmosphere, then condenses and precipitates back to Earth as rain or snow. Oxygen molecules are carried along in this cycle and can transfer between Earth's oxygen reservoirs is one half of the puzzle of how oxygen can record climate. The other half is that oxygen isotopes have different weights. Before we keep going, here's some quick oxygen isotope anatomy. An oxygen isotope must always have 8 protons, but can vary in the amount of neutrons. The difference in neutrons creates the common oxygen isotopes O16, 8 protons and 8 neutrons, and O18, 8 protons and 10 neutrons. O16 is about 12.5% lighter than the heavy O18 oxygen isotope, and the ratio between these two isotopes in ice, marine sediments, or fossils is what gives scientists a window into Earth's past climates. Let's go back to our 3 reservoirs. Each isotope transfers differently between each of them. The light O16 oxygen isotope easily evaporates from the ocean to the atmosphere, and the heavy O18 oxygen isotope easily condenses from the atmosphere to the ocean or ice as rain or snow. Kinesthetic learners, this one's for you. To understand this, imagine you're holding a golf ball and a ping pong ball. The heavier golf ball represents a heavier O18 oxygen isotope, and the lighter ping pong ball represents the lighter O16 oxygen isotope. Throw them upwards with the same force, and the ping pong ball is much easier to throw because of its lighter weight. This demonstrates how the water molecules with O16 oxygen isotope evaporate out of the ocean easier than water molecules with a heavy O18 oxygen isotope. Now, if you drop both balls through a piece of toilet paper, the heavier golf ball, which represents the heavy O18 oxygen isotope, should break through the paper while the ping pong ball is simply caught. This demonstrates how water molecules with a heavy O18 oxygen isotope condense out of the atmosphere easier than water molecules with a lighter O16 oxygen isotope. Now let's imagine a past Earth with a cold climate. This arrow I'm drawing indicates the small latitude range of warm temperatures, which is limited to near the equator. When Earth had cold climates, the oceans are mostly water with O18 oxygen isotopes, and the ice had mostly water with O16 isotopes. While O16 and O18 evaporate from the oceans to the atmosphere equally in the high-energy warm temperatures near the equator, as atmospheric circulation moves the clouds from the equator to higher latitudes, and this process is mirrored in the southern hemisphere as well, the colder high-latitude temperatures do not have enough energy to keep the water with a heavy O18 isotope from condensing and precipitating back into the ocean as rain. Only the water vapor with the light O16 isotope can make it past the colder climates and reach the poles, where it is precipitated as snow to form the ice scientists use to measure oxygen isotopes today. Now let's imagine a past Earth with a warm climate. This arrow I'm drawing indicates the large latitude range of warm temperatures, which nears the poles in a warm Earth. When Earth had warm climates, the oceans had more water with O16 isotopes, and the ice had more water with O18 isotopes. With higher energy, warmer temperatures reaching the poles, water molecules with a heavy O18 isotope were able to stay in the atmosphere for longer and condense at the poles as snow to be trapped in the ice. In addition, in warmer climates, the ice at the poles would melt. This released the light O16 isotopes that had been stored in the ice in past colder climates back into the oceans, diluting the ocean's previous heavy O18 isotope concentration. So, what we learned is scientists know that Earth had cold climates when they can date and measure relatively high rates of O18 to O16 ratios in ocean sediments, and when they can measure relatively low ratios of O18 to O16 in ice cores at the poles. Scientists know that Earth had warm climates when they can date and measure relatively low ratios of O18 to O16 in ocean sediments, and when they can measure relatively high ratios of O18 and to O16 in the ice cores at the poles. With this relationship between oxygen isotope ratios and Earth climate, paleontologists and climate scientists have established a level of certainty about global climatic context of many stages of Earth's past. With this video, you will be able to lend a hand to any earth scientist student, that's me, or their earth science professors who still struggle with this complicated topic, and they, me again, will love you for it. Thank you!